First, let me introduce Dr. Kevin Gurney to you. Dr. Kevin Gurney will present an overview of Soccer 2, Chapter 4, Understanding Urban Carbon Fluxes, and will take a deeper dive into aspects of the urban carbon cycle related to quantification of fluxes, atmospheric monitoring, and urban scale inverse modeling. Together, these elements are being conceived of as a potential greenhouse gas flux information system for cities. He will also provide a description of new and continuing efforts at the national and international scales, focusing on the urban carbon cycle and how new monitoring and modeling efforts are attempting to meet stakeholder needs both domestically and globally. I have known Kevin since his work serving on the science steering groups of the Global Carbon Project and the US Carbon Cycle Science Program over 8 years ago. It's been a pleasure working with him on Soccer 2 the past few years also. Kevin, thank you for your willingness to speak with us today. Please start your presentation now.
Sure. Well, thank you to Gurney and Tracy for inviting me to give a talk. And thanks to Soccer 2 in general for the excellent work that they did. It was a pleasure being involved. As Gurney mentioned, I'm going to talk about Chapter 4. It's important to mention my co-leads. I'll list them at the end, but my co-leads on that chapter, Patty Romero-Lancao at the National Renewable Energy Laboratory and Stephanie Pinchel at UCLA. I'm going to just quickly review the highlights of the Chapter 4 on understanding urban carbon fluxes, and then go into a little more detail on the particular piece of that topic that I've spent a bit of time on, which is systems, information systems, measurements, and modeling to better understand urban carbon fluxes and hopefully be useful for both science and stakeholders. So first, a few of our key results from the urban carbon flux chapter. It's always worth emphasizing the fact that urban areas globally, and particularly in North America, are the primary source of anthropogenic carbon emissions. Cities are responsible for a large proportion of direct emissions. That number is difficult to quantify, but roughly speaking, it's between 2/3 and 3/4 of the total carbon flux. And there are also large areas of indirect sources. So those would be emissions that are occurring outside a city boundary, but driven by, for example, let's say demand of goods and services within, embedded in goods and services. The drivers of emissions, there are a variety of societal factors that drive urban carbon emissions: the urban built environment, the regulations and policies that shape urban form, that is, the things that make up the particular land uses and their configuration within an urban area, and of course technology. Things like modes of transportation or building design all play important roles. And because there's so much large-scale infrastructure in cities and is so deeply involved with the emissions profile within cities, they experience this infrastructure lock-in, which can be decisions that will dictate a certain level of emissions over a long period of time once infrastructure decisions have been made. And this plot to the right just shows on the x-axis equipment lifetime, so things like power plants, transportation systems, ships and boats, and the cost, a low carbon replacement cost on the y-axis. Just showing that there's a lot of long-lived equipment that is not inexpensive to shift, and hence those decisions are both of large financial implication and have large carbon lock-in implications as well. Key challenges for studying urban carbon fluxes are building observational design systems, models, and integrating all of that with adequate uncertainty quantification, and then getting them all to be coherent with one another within urban areas remains an important piece of work that's ongoing. And again, I'll dive a little deeper into that topic in later slides. Also, cities though many are interested in reducing greenhouse gases, it's clear that a lot of the attempts to do so have to be part and parcel of other elements that are important to cities, that is, co-benefits that might be associated with air quality, human health, things like urban heat island, and many of the other important environmental targets that cities have. Urban methane, distinct from CO2, have been poorly characterized in comparison to CO2, but there's been a tremendous effort in the last few years, both in cities and without, as many people know, to improve instrumentation, measurement, modeling tools, and a lot of interest in that problem, given that, unlike CO2, it's sometimes almost an unintended side product of activity, and hence it's important to try to stop the fugitive or unintended loss of methane from, for example, piping infrastructure and such within cities. And then finally, cities are important sites for policy and decision making, not only because of the magnitude of their emissions, but because of the potential autonomy they have in passing policy. However, it's always important to remember that cities, somewhat different from nation states, are embedded within most often, other levels of governance at larger spatial scales typically. In the United States, as an example, and this is true both in Canada and Mexico, cities are embedded within, there might be counties, regional planning authorities, then states, and then of course nation state constraints as well. And so though they have autonomy, it's important to understand the relationships that they have to those larger scales of governance and understand how to enact mitigation policy that's integrated with those other scales. There's a tremendous amount of work going on in North American cities. I know that you can't see these tables, and I put them up merely to just try to show the list that we had put together at the time of the soccer publication. And this list includes cities in which there is not just simple, let's say, self-reported inventory efforts. Many, many cities are doing that. But this is a list of cities that are having what, let's characterize it as fairly intense scientific study. And even since the Soccer 2 report, this list is growing. And of course, you go outside North America, and there's plenty of other cities doing this as well. And by that, I really mean measuring and monitoring with scientific-oriented instrumentation, modeling, usually with collaboration with academic institutions in many of these cities. And some of these are in collaboration with city stakeholders as well. So I'm going to now jump into this deeper dive, as we'll call it, into urban emissions quantification and the architecture that is emerging to tackle that problem. And what I'm showing here are three pictures that is an attempt to show what we're trying to turn into a singular system. And I think it's getting pretty close. In the upper left, and I'll see if I can grab the cursor. In the upper left is the Hestia quantification system, which is a real bottom-up, very detailed attempt to quantify emissions at very fine scales, building and street level scale for a whole city. In this example, it's the city of Indianapolis, where a lot of this work, at least in the United States, was begun. In the middle is an example of then emissions like that being transported through the atmosphere. And in the lower right are examples of measurement technology. So tall towers with instruments that would be measuring, for example, CO2. And then you can even see an aircraft in the upper left of that lower photograph that will be measuring fluxes as well. And the attempt here is to combine all three of these elements into a singular system to potentially verify mitigation policy, offer mitigation guidance. In other words, with a very detailed picture and mapping of CO2 fluxes in a city, it would lead to potentially very efficient solutions by being able to target the largest emitters in a given landscape. It's also leading to a lot of science that I won't go into, but is very much part of the topic of urban metabolism, understanding cities as kind of metabolic units. This is just a bigger example of that bottom-up CO2 inventory, just trying to make the point that in addition to getting a better quantification of whole city emissions and their trends, this type of detail can provide an awful lot of information potentially for cities to target large emitters or portions of a city that might intersect with other interests of policymakers in a city. For example, retrofitting buildings in low-income building envelope portions of a city. That's a small subset of the landscape, but it's important to know the intersection and detail of those two topics. The type of work I've described, this attempt in combining top-down or atmospheric measurements with models and bottom-up inventories, has begun in a number of cities in North America. And the upper left is Indianapolis, the first city that I've been involved with that was doing this type of work. And there's many institutions that have been involved in that, and that's true in all these other cities as well. The upper right is Salt Lake City, where similar work is ongoing. Lower left is Baltimore. Lower right is the large LA megacity domain, which has a similarly large project, which in addition to some of those measurement assets I showed in that previous slide, has an overflight of OCO2. So there's some satellite technology being used in that domain as well. And then, though I don't have a picture, it's important to recognize Boston, in which there's an awful lot of work going on with BU and Harvard University and city stakeholders in that urban domain, and then a variety of efforts. Of course, outside North America, I've just listed 4. There are others, but I've listed 4 that are pretty active right now. Melbourne in Australia, Auckland in New Zealand, Paris, which has had a long-standing effort, and a new effort starting up in Sao Paulo. And as I said, there are others as well. Some of this work, at least in the from that very detailed urban scale, sits inside of this larger flux quantification effort. And I'm going to mention this because we're doing some new things that are relevant to cities from this effort. In some ways, this preceded that very detailed city effort, but it's become so detailed now that it's starting to converge with some of the urban work, even though it attempts to quantify, in this case, CO2 from fossil fuel combustion across the entire U.S. landscape. But we're now doing this at about a ½ kilometer every hour for multiple years, and even going beyond the classic scope 1, which is emissions that occur physically within some bounded piece of the landscape, right? So that is not the indirect emissions that might be arising, let's say emissions in a factory in China given consumption in some city here in the US. These are just the direct emissions in a bounded area, but we're also including scope 2 at this point. Now, scope 2 is emissions just driven from electricity production, but allocated to the point at which electricity is consumed, as opposed to where it's leaving a smokestack at a power plant. Now, I'm showing this larger landscape, which doesn't, again, seem like an urban topic, only because we are now carving out, because of the detail we're able to do it, carving out cities across the entire U.S. landscape. And indeed, we now have effectively scope 1 and scope 2 inventories for every single city in the United States at about this ½ kilometer scale. Not as detailed as that work I showed you previously, which has only been done in a few cities because of its extreme intense effort to go down to the building level and measure a lot of places. But this is exciting just because we're able to, in one fell swoop, generate an inventory for every single city in the U.S. And I'm just showing some examples: San Francisco Bay Area, Sacramento, some of the Central Valley. This is the Houston urban area, Boston and Providence, and a little bit into Connecticut urban areas, the big New York, Philadelphia corridor, and then finally Washington, D.C. And important just because, as I'll show in a minute, cities have expended a lot of effort to generate their own what we call self-reported inventories. That's been an important piece of work ongoing, somewhat independent of this scientific effort, but we're hoping to use some of what I just showed you to obviate a lot of that work in the future. Now, an important piece of putting those three elements together, the measurements in the atmosphere, that transport modeling, and those detailed bottom-up inventories, is the inversion. And it's really just a way that kind of glues, if you will, all these pieces together and tries to get them to be internally consistent by adjusting those flux maps to be consistent with what we measure in the atmosphere. And the atmospheric measurements are crucial because they're probably the most accurate thing we can measure or monitor in cities. And they're a perfect integrator of activity at the surface. And of course, inversions have been done at many, many different scales. And indeed, the work at the city scale is in some ways just a remapping of efforts that have gone on for 30, 40 years at the global scale, doing this down at the city scale. This is an example. It's a bit of a busy plot, and I'll just quickly tell you that the punchline here is just the lots and lots of boxes that are off that kind of axis towards the bottom were just different ways of setting up the inversion. It itself has uncertainty in terms of how it gets set up. The kind of length scales you use for influences of measurements, and a variety of details that aren't so important, but at the top is the kind of central estimate that comes out of that. And the two darker boxes that are off to the left are just two different bottom-up estimates. And in fact, one of those bottom-up estimates is the Hestia estimate that is a little bit different from the inversion estimate. And there's an example of where the atmosphere might suggest an adjustment to the bottom-up detailed flux effort from the bottom. But it's important to get those things to be looking at the exact same CO2. And we're still working on this, and this is just an attempt to show some adjustment of those fluxes to make sure that we're comparing apples to apples. And the example here is that the atmosphere is going to see all parts of CO2, not just the human, let's say, fossil fuel combustion coming up from the city, but it will see human respiration, it will see a bit of biotic respiration. In this case, that inversion was run over the winter, so we didn't expect a lot of photosynthetic activity, but cities are heavily managed. There's a lot of soil and urban vegetated landscape that respires even into the winter. And so this another busy plot was just an attempt to show that when we try to include a bit of what we think is those missing fluxes that is different between what the atmosphere sees and what the bottom up estimates, we actually get very close convergence between the atmospheric measurements and the bottom up detailed estimate of fluxes. And in fact, since that work, which was in 2016 and 2017, we've updated our systems, and this is just a very recent example, unpublished work, that shows, and I'm just going to focus your attention on the upper left. Now that's over time, the Hestia, or very detailed bottom-up emissions estimate, is this black line running through. There's a bit of seasonality in the fossil fuel CO2. And now the inversion, atmospheric inversion, because we've improved our systems, is almost sitting perfectly on top of that bottom-up estimate. Something that I think surprised all of us, that we're now getting, at least in this one city where we've expended an awful lot of effort, very almost near perfect convergence between these very different estimation systems. Which means we can go forward with kind of the best of both worlds. The accuracy that the atmosphere offers in the detail and process information that the bottom-up inventories we're building offers as well. And the combination of the two really can give cities an awful lot of information, we think. Now, we've taken all of those urban estimates I showed from that large U.S. landscape in which we carved out all the cities, and a useful and curious thing to do would be to ask, since many cities have been doing their own inventories using fairly standard methodologies, although there's 2 or 3 out there now that are used most commonly. Again, these are very distinct from the intensive efforts that we've been doing in a few of those cities. But if we took all of those self-reported inventories and we directly compared them to the detailed bottom-up effort from Vulcan in which we carved out all the cities, we're finding significant differences between those self-constructed inventories and what we're building through the techniques I've showed you previously. This just emphasizes the point that there's still a tremendous amount of work to be done, and I think a lot that science has to offer to this to the policy and urban carbon management effort, because there's still a lot of discrepancy between what cities are constructing for themselves and what we think is actually occurring in most of these cities. We still haven't unraveled why this is, but we have a few ideas. So with that, I'll stop. Here I want to list, again, Patty and Stephanie, my co-leads. There were about 15 to 20 co-authors on our Chapter 4. I haven't listed them all here, but I have put pictures of my group members just to acknowledge their contribution to some of the work I've just showed you, and of course the people that have funded some of the detailed work that I just showed you. So with that, I'll stop, and thank you very much.
Thank you, Kevin. That was terrific. And you already have some questions. Jim McMahon asks, the recent unpublished data that you just showed, what city was that for?
It was for 57 cities. Each one of these bars is a city. I covered it up just because it's not public yet, and typically when I don't cover it, people get a little bit distracted by the exact city, and because we still have work to do to make some fine adjustments with trying to make sure we are characterizing each one of those cities' fluxes correctly from those self-reported inventories. I've covered them up, but it's 57 cities. It runs the gamut of size, everything from smaller places like Boulder up to New York City is sitting on this plot, and those are percentage differences. And I didn't go into a lot of detail, but the mean absolute percent difference is closing in on 50%. The mean sign difference is about 24%. So just as I say, pretty large differences, well outside the uncertainty that we think we can estimate city fluxes with, and hence I think we have a lot to contribute.
Okay, and you have a follow-on question from Jim. Have Vulcan estimates been compared to any state inventory estimates?
Yes, so we will compare it to the EIA-derived state flux estimates. We're within anywhere from 5 to 12% at the state level. There are reasons why we would be different from those estimates. The primary difference is that the EIA is characterizing kind of fuel delivery into a given location, and because fuel can move once it goes into that location, Vulcan attempts to capture that fact. Vulcan is really looking at the absolute endpoint of combustion. So we think those differences are explainable by the fact that they functionally are trying to target different things, but we actively compare Vulcan at every scale we can to independent estimates.
And then we'll take one more question from Ron Larson, and then we'll move on to Guillaume's talk, and then we can take additional questions in the end if we have time. Did you also provide your email, right? We'll provide it if that's okay.
Yeah, sorry about that. I don't think I put it on that last slide. Forgive me.
So Ron asks, what are plans to include the reverse carbon dioxide removal?
In plans to include it in the bottom-up type of estimation. I mean, we're certainly attempting now to include vegetative fluxes in both directions, and if there's any human-driven CO2 removal, we would intend to capture that in our estimation procedure. We want to, if any flux, regardless of the direction, is occurring within an urban domain, we want to characterize it in our information systems. We want to essentially quantify every molecule regardless of its direction within those domains.
Okay. Well, thank you very much, Kevin. That was terrific.